Hi, so now we will again perform 1D modeling using MBAL software. So let's talk about it. We are here in MBAL and then go to Tool, select 1D model. And then for options, we select reservoir fluid oil. If you open the drop-down menu, there's only oil. Injection fluid, either water or gas. We select gas. We select water, I mean. And then fluid model, we can do enter fluid properties. And I'm going to show you, click done. PVT will be deactivated. Open input, reservoir parameters. You can now provide the PVT data here in this section. Okay, cancel. But if you select enter fluid model, done, then now the PVT option is active and you can input the PVT here. And if you have laboratory data, you can also do perform matching for the PVT data to compare between the laboratory result and the computation. All right, let's start simple here. So I prefer using enter fluid properties. EOR type is none. I will perform water injection first and later on I will conduct EOR with surfactant. Okay, so click done. Okay, so PVT option deactivated. Click on input, parameters. Now we need to populate this window with data. Injection. Let's say it's a pilot testing. I want to start with relatively low injection rate of 200 stock-chamber per day. Start of injection January 2023. Okay, and we will keep this data. They are reasonable values. Oil density 50, and then oil viscosity 5, right? Formation volume factor 105. Water density 60, good. Water viscosity 1, all right. Water formation volume factor 1, yes. And reservoir length 100, width 100 feet, height 50, good. Oil water contact 50 feet, deep angle 0, horizontal reservoir, good. Permeability 100 millidarcies, okay. And porosity, let's say 0.25. Connaught water saturation, let's say 0.25 as well. Okay, cut off water cut. Yeah, we perform water injection and we perform enhanced oil recovery. Okay, let's expect that we will allow water cut to be as high as 99%. By allowing very high water cut, of course, you can extract more oil, right? But of course, later on, you need to assess or you need to perform economical analysis to come to make sure or to conclude whether it is a good operation decision to allow your water cut to be as high as 99%. Okay, and number of cells 100. Okay, and then relative permeability. So this is the default value. Let's plot it. Okay, so it's a straight relative permeability. Let's reconstruct the plot. This one and then so like this. Okay, so basically you can have linear relative permeability for fracture zone. So yeah, maybe we can play a little bit with this. So let's say, okay, endpoint for the oil and for the water, exponent 2 and 2. So it's like this. Okay, yes, it it looks better than having the straight line relative permeability, right? Okay, so this is the case. You can also convert it to table, or you can also provide data in tabular form like this if you have the data, or if not, you can simply construct the relative permeability plot, relative permeability curve using Corey functions like this. Okay, so click done. All right, and then let's just perform the calculations. run simulation, calculate. So it's very fast. So you see, we have water breakthrough 2 years after injection. So 2024, we will have breakthrough where the pore volume injected reaches 0.3365. And at that point, we have achieved recovery factor of 42%. And yeah, after 2.9 pore volume injected, okay, you can achieve recovery factor 57%. And of course, you want to increase the recovery factor, right? Okay, this is the volume of water injected, oil produced, and water produced. Okay, here is the reservoir properties. You can also have the computed mobility ratio. So it's 2.5 greater than 1, okay? So water is more mobile than the oil, and it's not very good actually. Okay, so what else? Yeah, so this is the fluid properties and reservoir saturation. Okay, click finish. So remember, we have recovery factor of 57%. Click finish. You can also show the result starting from January 1st, 2023. Go down, you can see a recovery factor of 57.43. Okay, and you can track also the pore volume injected, average oil rate, water rate, and so on and so forth. So let's plot. Okay, I'm going to delete these cases. Yeah, okay. All right, so here, calculated, pore volume injected, and then let's check average oil rate, okay, and the water cut. So water cut like this, first zero water cut and then breakthrough, water cut increases rapidly. You can also plot it with oil rate. So the oil production decline is because of, the water breakthrough and increase of water cut. You can also check water cut and water saturation. So it's like this. Okay. And lastly, recovery factor. So here, 57%. Okay. So let's save that and then let's add the case. I want to add case of using surfactant. Or maybe we can click done first and then let's perform the second case. So remember 57% the recovery factor. And now let's change it to surfactant. Okay, click on done. So now, in addition to parameters and relative permeability, we need to input EOR input and enhance oil recovery schedule. And in parameters, we need also to input grain density. So I will input 1.2 gram per centimeter cube. So that's good. And also the injection rate 200, porosity 0.25, and contact water 0.3. Okay, right? Okay, so now relative permeability 1, 0.5, and then it's 2. Sorry, it's 2. So we maintain everything the same, but now we perform enhanced oil recovery with surfactant injection. So the plot will be like this. Okay, for the relative permeability. And then, okay, so good. EOR input. Okay, so now actually we need to provide data for polymer and the surfactant. Of course, in this case, I'm not going to perform polymer injection, but you must provide the data. Okay, so whatever I write here doesn't matter. Okay, and let's focus on the surfactant. So we need to provide surfactant concentration in ppm, all right, and then the surface tension in dyne per centimeter. So let's say we already input the data here for our surfactant. Okay, 0 ppm, surface tension 1125, 100 4.11, 500 0.312, and so on and so forth. And let's assume rock adsorption and oil partition coefficient to be 0.001 milligram per gram. Okay, so that's good. Now let's go ahead into the EOR schedule. So I will make no polymer injection by using this for volume injected 0, polymer concentration 0, so no polymer at all. And then, yeah, just like this. And for the schedule of surfactant injection, let's assume I do like this. So at 0.1 or 10% per volume injected, I inject the water with no surfactant in it. Okay, and then the next per volume injected 0.2, 100 ppm. I just follow the data here because we don't have data for, you know, greater than 5,000 ppm. So let's assume, or you can also, based on your planning, you just, you know, put the schedule here. 0.4, 500, 0.6, 1000, 0.8 to 50 to 2500, 1 per volume injected, 5000. Okay, so let's click done. And we expect that the recovery factor can be increased. Calculation, run simulation. Okay, just we need to make sure what we write previously. Okay, injection rate 200, Conat water saturation 0.3, porosity 0.25. Okay, calculate. So this is water saturation versus length. Okay, now we already achieved 52%, 55%, 60%. Oh, it's good. And the computation done, right? So now, oh, but we need to adjust the date here. It's not quite right. I'm just going to make it, yeah, this one. Okay, it's not important, but I would just want to make it like that. Recalculate. So as you can see, having or performing surfactant injection with that surfactant increase, the recovery factor significantly from 57% to now 72%. It's actually very good. The breakthrough in 2024, okay, at per volume injected of 0.3365. And you see here, recovery factor 72. It's great. Okay, and let's just go to plot result. 72.57. So if I can click save, oh no, yeah, right, 72.5758 plot. So you see there is, interesting. The water cut changes are very, very interesting. Okay, maybe because of, the change in surfactant concentration that we use. Water saturation like this, water cut like this. Okay, and for volume injected, average oil rate. Okay, and then of course, the most important thing, recovery factor, greater than 70%. Okay, And yep. Okay. And let's try another interfacial tension. Let's say we want to compare with another surfactant. Okay, we can easily do that by going into this. Okay, maintain everything the same. And then let's just change it to 3.97, 0.633, 0.00337, 0.0, I mean, and 0.0046. I maintain the same schedule and then click done. Calculation. Previously we have 72%, 72.58%. Now let's calculate and hope for the best. Okay. Still far away from 70. Oh no, it's even greater. Now we can achieve recovery factor of 78%, right? At pore volume injected of 1.77. It's great. Okay, so right, that's great. We can check the result. Okay, it's recovery factor 78%. Water saturation. Oh, water saturation follows the trend of recovery factor. Okay, good. Water cut. Interesting. Water saturation. Okay, and then average oil rate. Okay, frontal fence. Okay, okay. So yeah, that's it. So in this video, we have conducted 1D simulation using MBAL software for 3 cases. The base case is we conduct water injection, and the next one we perform surfactant injection with surfactant that we have. And the third case is that we use another surfactant, and based on the computations, we can conclude that although water injection can give us recovery factor that's quite good, greater than 50, but of course, having surfactant, having in particular those surfactants improve this recovery factor significantly. First, the first surfactant gives you 72% recovery factor, and the second surfactant gives you 78% recovery factor. That's very great. Okay, so that's all. I hope you enjoyed this video. I hope this video is useful, and thank you so much. See you again.